Okay, it's 3:05, so let's get started. So quiz 5 is out. It's due Saturday. I still highly recommend starting these as early as possible, but it's due on Saturday just like usual. Second part of homework 2 is due Sunday. How many of you did something about homework 2 part 1? Okay, so for those of you who haven't, I still highly recommend doing these even though they're not worth credit. They give you really good feedback and all that stuff. Any questions before we start? Any questions about anything?
Well, I'd ask you about the pumping lemma, but I think we're about to talk about it.
Yeah, for about 45, 50-ish minutes. Yeah. Any other questions? Anything specific?
Lay it on me.
Just do all of it, right? Okay, so what was the main thing we talked about in lecture last week then?
Pumping.
Yeah, pumping, right? As was the given suggestion. All right. So what does pumping lemma do? How does it help us?
It allows us to show that a language is not regular.
Yeah, it helps us show things to be not regular. But what does the lemma actually say? Like in English, what does it actually say?
That you could split this string into 3 different pieces.
Before we even get to there, way before that, right at the very start, what does it say?
L.
L is?
Yours.
It says something about L being.
Oh, assume that L is regular?
Yeah. So for proving something non-regular, I assume it's regular. Why do I do that?
Because you're about to prove a contradiction.
Yeah, but what if I just started from the beginning? Do I need that assumption? Yeah. So what does the lemma start with? It only says things about regular languages. Okay? So it only says something if L is regular. But if I said, I want to show that this is not regular, I can't apply the pumping lemma directly. So what do? I think I do a proof by contradiction, right? I assume it is regular, then I can apply the lemma, and then I get a contradiction, and oops, my assumption was wrong. So if I assume L is regular, what can I immediately say in terms of the lemma? Well, what does regular even mean?
There's one.
There's a DFA for it.
There's
There's an NFA for it.
Right, there's everything for it, right? Well, what does the lemma say here? There exists what? Some constant, this weird constant thing, right? So exists a pumping constant P for L. But why is that in there?
For the length.
That's the guarantee that you repeat a state in a DFA.
Ah, I want to repeat states in the corresponding DFA. So what in the world does this P represent? Number of states in a DFA for L. Okay, so I'm thinking P to be the number of states. Well, why do we want to repeat states? Because if I repeat a state, can I go around that loop, the state to the same state loop, as many times as I want and still stay in the language? Yeah, I can just go around that loop as many times as I want. So the pumping lemma actually says things, when you have a string in the language, it says things about other strings in the language. It tells me about the structure of strings in the language. Okay, well, let's see. Well, does every string that does this repeating pattern and be accepted, can I pump that string? Yeah, because it repeats a state, so I can go around whatever loop that is as many times as I like. So I better say that this works for all W and L. But how do I guarantee that a state repeated? What do I have to guarantee about W? What if it's like one transition? Do I guarantee that a state repeated?
So we divided it.
Not necessarily. What do I have to guarantee about W itself?
Bigger than P.
Right, it better be so long that I have to repeat a state, no matter what happens. I may repeat one on the very first transition, but I have to guarantee it for every single DFA, every string. So I think I better have length at least P than number of states. So for every single string with length at least the number of states, or at least P in this case. Yeah.
Do we need to specify P, that P is equal to N?
What does that?
Number of states in the DFA for L?
I'm not talking about DFAs here. There exists a constant.
Because we don't need to specify anything about P.
Nope.
It's pretty-
All I assert that this P constant exists. Okay. Well, let's see. For every string that's long enough, I can do this repeating pattern. So let's think about what the DFA looks like then. So let's suppose that this state in the middle is my repeating state. And I said that it's in the language, so I think it has to end up in a final state. So let's say the final state is here. And it's kind of misleading. All three of these states could be the same state, or all three could be different, or two could be the same. But I know that I'm just doing it conceptually. So I said that this state repeated, so there must be some way to get from the start state to the state that repeats. And let's call the string that is the transition labels put together X. Well, I said that that state repeated, so there must be a way to go out and come back to that state, because I said it repeated. Let's call that string Y. And I said that the string has to be accepted, so it has to go to some accept state from the repeating state. Let's call that Z. Okay? From this, can I say that X, Y, Z is in the language? Yeah, because X, Y, Z. What about X, Z?
Yeah.
Yeah, I don't have to go around that loop, right? What about X, Y, Y, Z? X, any number of Y's, Z. Yeah, just follow around that loop as many times as I like. Okay, well, let's see. Well, there must be some way to, if I have a string that like this that does have this loop, there must be a way of writing it as those three parts. So there is a way to write W as X, Y, Z, so that, and then we have three conditions on it. Well, I think we just agreed that X followed by any number of Y's, Z is in the language. So how do I write X followed by any number of Y's with Z after?
X, Y, star.
Yeah, so X, Y, star, Z. I'm not going to be talking about regular expressions here because that's a regular expression. I want an actual string. So I think another way I could have written this is X, Y to the I, Z is IL for all I at least 0. It needs to work for every single value of I, right? Because no matter how many times I go around that loop, as long as I read a Z afterward, I accept, no matter what. Okay? So what in the world are the other two conditions?
X plus Y has to be less than P.
Yeah, the length of X, Y together is at most P. So why in the world is that true? Well, let's see. I said that this works for any string of length at least P, right? Does it work with strings of length exactly equal to P? Yeah, I just said at least P. Does it work for things of length exactly P? Yeah, so let's think of a string of length exactly P. That's in the language. Does it repeat a state? It has to repeat a state because it works here, so it must work for strings of length exactly P. So there must have been repetition in the first P characters. There are only P characters, but there must have been a repetition. Consider a longer string then. What about the first P characters? They have to repeat a state, right? Because if I just consider the first P characters of that longer string, I still repeat a state. Okay? So, what is the repeating part? The repeating part is y. So, y can't end later than the p character. Right? It may be the p character it ends on, but it can't be later. Oh, but that also tells me that x comes before y, so that must mean the length together can't be longer than the p character of the string. So that's how we get this. This condition ends up not being completely necessary. We don't need it, but it's extremely useful otherwise. The second condition we actually do need. So what is that second condition?
Y is bigger than 0.
Yeah, so length of y, I'll say equivalently, is at least 1 in length, or y is not empty. So why is that one true? Why? How come that's true? Well, let's see. I can actually show it in 2 ways. Consider the repeating state in the computation on the D at A. Well, that state repeated somewhere. What is the closest it could have been shown again in the sequence of the states that I visit? Well, the next one is the shortest one I could have been to. How many transitions is from there to there? At least 1, right? Can any transition be empty? No, why? It's a DFA. So no transition is empty. So this loop has to be non-empty. Maybe more than 1 character, but it has to be at least 1. Another way you can prove it is, consider if it were empty. What would this third condition tell me? Well, if I enter a whole bunch of copies of the empty string in the middle of xz, is that going to change anything? No. So therefore, I can pump every string. And I don't want that. So I need y to have non-empty length. Okay? Any questions about this? So now let's actually prove things. So let's start working on the problems. So the first one is, well, we had 0 to the end, 1 to the end in lecture. Let's just extend it a little bit. So 0 to the end, 1 to the end, 2 to the end. And I claim that this is not regular. Oh, shoot. This says that it's going to be non-regular, but pumping lemma only works when it is regular. I can't apply it. Oh, or wait, can I? How can I?
Assume it's regular.
Assumes.
Okay, let's assume it's regular. L1 works regular. Oh, now based on my assumption, now I can apply the pumping lemma, so we're good there. So what does the pumping lemma now immediately tell me? What does it tell me?
That there exists a pumping.
There exists a pumping constant. So I'll say there exists a P for L1. Okay? Remember, I want to get a contradiction out of this. So let's see what it says. It says that for every string in the language with length at least P, I can pump that string. There is a way to pump that string. But if I can show you somehow that one example doesn't work, I can't pump it for sure, what does that tell me?
The language isn't regular.
It can't be regular, because if it were regular, every example would have worked. It says for every single string W. So I think if I can pick one that doesn't pump, we're all good. So now I gotta choose a string. So I gotta choose W to be some string. What are the 2 qualifications on this string that I need?
In the language.
In language and
At least.
long enough. So what if I do this string? It's in the language. That's no problem. Is it long enough?
Not necessarily.
Not necessarily. P may be very large compared to 3. So how can I fix this?
We can add some exponents.
Yeah, add some exponents. So what exponent should I put?
P.
P. works perfectly fine. So P, B. Well, let's see. Got to do our two checks again. Is it in the language? Well, equal number is zeros, ones, and twos, and that's what I have here. Does it have length at least P?
Yes.
Yeah, it has length 3P, so we're good. Okie dokie. So this is my candidate string. I don't know if it'll work, it will, but I'm just testing it to make sure, to see if it'll work at all. Let's see. For this string that I picked, it says that there is a way to write W as X, Y, Z so that I can pump the Y part. Well, let's see. I think I need to show that there is no way to choose X, Y, Z. If I somehow leave out one way to write it as X, Y, Z, that way may work, right? The pumping lemma says there exists a way to break up the string into X, Y, Z. To get a contradiction, I need to show you there's no possible way that it can work. Okay? Every way fails, essentially. So then now I gotta think, what are all the possible ways to break it up into X, Y, Z? So let's think about that. So X is gonna be something, Y is something, Z is something. Well, I know that X is at the beginning of the string, so it has some number of zeros, for sure. But could it ever hit the ones? No, and why is that?
First rule.
The first rule, right? The length of X, Y is at most P. Oh, the first P characters are all zeros. So that tells me immediately that X is all zeros. Oh, does that tell me anything about Y?
It starts with
It's
1.
also all zeros. Okay, well, even though that this condition is not exclusively necessary, it's very helpful. So now I don't even need to worry about whether X or Y hits the ones or the twos. And that'll be very useful for us. But then again, I still gotta have all possibilities of breaking up the zeros, or some of the zeros, into the X and Y part. So X is, again, I don't know how many zeros it has. But let's just say it has A zeros for some number A. Can A be 0 itself?
Yes.
Yeah, because I never say anything about whether X is empty. It could be empty, for sure. Well, again, for Y, it's some number of zeros, but it may not be equal to the number of zeros in X, but it's some number of zeros. But let's say it has B zeros. Is there anything I can say about B?
It's equal to P minus A.
A plus B is
I'm not using all the zeros here. I don't have to use all the zeros. But is there a lower bound?
A plus B has to be P, doesn't it?
At most.
At most P.
At most B.
B has to be at least 1.
Exactly. B is at least 1. And why is that true?
Because we have Y can't be empty.
Yeah, via the second condition. Good. So now I got to figure out what the Z part is. Well, the Z part is the rest of the string because I only have 3 parts of the string. So I think I started off with P zeros, took away A of them, took away B more of them. So how many zeros do I have left?
P minus A minus B.
P minus A minus B of them. So I have P minus A minus B is zeros. I never hit the ones or twos with X or Y, so I think I still have all of those. Okay? So now I'm starting to get quite toward the end of the board. So I think I should be thinking about what my contradiction is going to be. So what of the pumping lemma is going to help me get a contradiction really easily? Is there something we haven't used yet? Yeah, the third one, right? We used the first two to make all of the decompositions, but we haven't used the third one. So let's see what the third one says. It says that for the Y part, I can pump in as many copies of Y into the middle as I want, and I will always stay in the language all the time. Any number of Y's, I always stay in the language. But if I can find you an I such that I can get out of the language, this for all doesn't work anymore. And then what can I conclude?
That you have a kind
It can't be regular, because if it were, every single value of I works. But I'm going to show you one that doesn't work. Okay, so now we got to choose value of I. And for this one, it turns out every value other than 1 works. Why does 1 not work? Because how many Y's did I have at the start?
at least 1.
I have 1, right? And I already was in the language. I want to get out of the language, so I can't choose 1. So I'll let you choose any value other than 1.
2.
0, that's perfectly fine. So let's choose I equals 0. So that's x, y to the 0, z. What does a string taken 0 times?
Epsilon.
Epsilon. Good. So this is just x, z. What is that? That's just 0 to the a, just copying everything from above, and z. So 0 to the p minus a minus b, 1 to the p, 2 to the p. Okay. It's just copying things down. How many zeros do I have now?
You have p minus b zeros.
P minus b of them. Nice. P minus b of them. And I think I still have all the 1s and all the 2s. So what do I need to check with this string?
In the language.
Yeah, if it's in the language. If it's not in the language, what can I immediately say?
It's not regular.
It's not regular because I just found you a value of I for which I'm not in the language anymore. But it may be in the language. So what's the only way that this could be in the language?
B is 0.
Yeah, b is 0. So the only way that this could happen is if b is equal to 0. And so, is that a contradiction?
Yeah. Yes.
Yeah, because I concluded b is 0, but I had b at least 1 to start with. So, what can I conclude? I think that L1 is not regular. So, from this, I can conclude L1 is not regular. Any questions on that? Okay. Let's move on to a very slightly different one. All I'm doing is adding more zeros at the beginning and slightly more 1s. Okay? And I claim it's not regular either. So what's my first step?
Assume it's regular.
Assume it's regular. Let's do that. So assume L1 prime were regular. And then I think I can conclude from that alone that there is a P for L1 prime. Exists a P for L1 prime. I'm not writing pumping constant for space, but it is the pumping constant. Okay, so what's my next step?
Choose a string.
Choose a string. All right, let's choose a string. Well, could I choose the string that we picked before? It has length at least p. Could I pick that one?
It's not in the language.
It's not in the language. Can I pick it? No. So I can't pick a string that's not in the language. But could I modify that to work over there? Yeah, what string would I use?
0 to the 3p.
Yeah.
1 to the 2p.
0 to the 3p, 1 to the 2p, 2 to the p. So just a little bit of advice. 98% of the time I'd say this works. Anytime you see an n in the exponent, for the string that you pick, put p where the exponent is. Not always that this works, but most of the time it works. Okay, well, let's check. Is this string in the language? Definitely. Has it length at least p? Absolutely. So now, let's look at the decompositions. Are my x and y decompositions going to change? No, because I have even more zeros. So there's no way it could have ever hit the ones. So I still have some number of zeros for x, still some number of zeros for b. And let's remind ourselves that b is at least 1 again. It'll always be at least 1. But I think the z part changes. So how many zeros are in z now?
3p minus b minus a.
Yeah, so I have 3p, oh, not 3 to the p, 0 to the 3p minus a minus b. I didn't touch the 1s, and I didn't touch the 2s. Okay. So, what's my next step now?
Choose an I.
Choose an I. All right. So choose I equals something. So it'll turn out every value other than 1 again works here. So I'll let you choose another one. I mean, be adventurous.
22.
22. It's actually the highest one anyone suggested. So let's do 22. It'll work. All right. So let's see. I want x, y to the 22, z. Well, what is that? That's the x part, which is 0 to the a. And so I'm going to shorthand it here. I'm going to say 0 to the 22b. And then the z part, which is 0 to the 3p minus a minus b, 1 to the 2p, 2 to the p. All right? It's just copying each of the pieces in. How many zeros am I going to have? How many zeros do I have?
3p minus 21b.
Minus 21?
Plus 20.
Plus 21, right. I have a plus 22 and then a minus 1. So 3p plus 21b, 1 to the 2p, 2 to the b. What's the only way that this could stay in the language? Well, the only way is if the number of 2's times 3 is equal to the number of zeros. That's the only way it could have stayed in. So I think this number better be equal to 3 times that number. So that means 3p plus 21b is equal to 3p. So what's my conclusion from that?
B has to be 0.
B is 0. And then I still get a contradiction like I did before. And so I can conclude that L1 prime is not regular. Cool. Yeah.
How come we don't specify a condition on A for X over here?
Because like what I did here was just to make it concrete to know what the lower bounds were. I said we didn't use the fact that A is at least 0 here because I mean A is always at least 0. But it's just getting into the mindset of knowing that B is at least 1. Like we didn't use it there, but it's just reminding ourselves what it is. Okay. Any other questions? Okey-doke. Let's do now the more fun ones, the ones I find really interesting. So I'm going to make the language a little bit harder and easier at the same time. So easier in the sense that I don't have any 1s or 2s in this language. It's just a unitary language. But I'm going to make it so that the number of zeros is a perfect square. So the empty string's in there because it has like 0, a single 1's in there, a single 0's in there, 4 zeros are in there, 9 zeros in there, 16, etc. Okay? And I claim again that this is not right. So how does this start off? Assume it's regular. Good. Assume L2 were regular. And then what can I conclude from that?
There exists a p.
Yeah, there exists a p, pumpkin constant p for L2. All right. What's my next step?
Find a string.
Pick a string. All right. So I got to pick a string long enough and in the language. And I guarantee you, someone, if we put this on the midterm, would put this. P stands for perfect square. So this has, and it has length at least P, so we're good, right? What's wrong with this?
You don't know?
It's not guaranteed to be a perfect square. Is there a way I can guarantee it though? Could I put P squared up there? Sure. Nothing wrong with that. Well, let's check. Is P squared at least P? Yeah. Is this in the language? Yeah, and it's a perfect square in length, so we're good there. So now let's think about our decompositions. So X is something, Y is something, Z is something else. What do I know X and Y entirely consist of? Zeros, right? Not everything in life has to be difficult, right? I know the string's all zeros, so therefore the X part is all zeros. So 0 to the A, 0 to the B, and let's just remind ourselves B is at least 1. So what is the Z part going to be?
0, or P squared minus A minus B 0.
Yeah, P squared minus A minus B 0. Okay? Nothing new, nothing fancy here. So I let you guys pick the value of I both times before, so now it's my turn. So I claim that every value other than 1, I believe, can work, but I'm going to choose one to make our lives as easy as possible, and we'll see why in a second. So we're going to choose I equals 2. Or at least most of them will work. So what is that? That's X, Y squared Z. Well, what is that? That's just 0 to the A, 2 copies of Y, so again, that's 0 to the 2B, and then the Z part, which is P squared minus A minus B. So what does that simplify to?
P squared plus B.
Yeah, P squared plus B, yeah. So I have P squared plus B. Okay. What's the only way that that could be in the language?
P squared plus B is a perfect square?
Right. The only way it could be is if P squared plus B is a perfect square. But it doesn't seem immediately obvious, like the other ones were, that this is not a perfect square. If I can prove it isn't, then we're good. But it doesn't seem obvious to me at this point. Okay, well, let's see. Let's look at P squared plus B. So I'm not worried about the string, I'm worried about the length itself. Maybe we can compare it to some perfect squares we know around there, and maybe we can see it's not equal to any of them. Okay? Is P a fixed integer?
No.
Yeah, can it vary? No, because I fixed it right here. There may be many values that it could work, but I fixed it right here. Can B be different?
Yes.
Yeah, it could vary across many different values. So, what is the smallest value that B could be?
1. 0.
1. Could it be 0? No, why? The length of Y is at least 1. So I know that this is at least, but it could be equal to P squared plus 1. Okay? What's the relation between P squared and P squared plus 1? I think it's an inequality. Is it strict?
Pretty strict.
It's a strict inequality. Yes. Because there's no value of P for which P squared is equal to P squared plus 1. So, can the length of my string be equal to exactly P squared? No, there's no way. And so, can I immediately claim that this is not regular? No. It may be equal to some other perfect square. Okay, well, it's not equal to this one, and it's larger than it. Maybe we can find out what, say, the next perfect square is. So what's the next perfect square after P squared?
P plus 1.
P plus 1 squared. All right. So let's figure out what this is. So cast your days back to middle school algebra. Let's put that hat on, right? What is P plus 1 squared?
Squared plus 2p plus 1.
Right, it's P squared plus 2P plus 1. Okay, well, I still don't see a connection between these two things, right? Oh wait, what is the largest value that B could take on?
2p plus 1.
Could it take all the way up to 2P plus 1? Let's look over here. It can't be more than P for sure. Can it be equal to P?
Yes.
Yeah, it could be. So I know that, therefore, that this is at most P squared plus P. Okay. Well, how does this relate to this? I have more P's and a plus another 1. So I know that there's another inequality right here with P squared plus 2P plus 1. Is it a strict inequality, though? I think so. If P is not 0, I think the 2P wins here over P. But if P were 0, it can't. But let's just assume it could be 0, and the plus 1 gets me. And that's how I prove it. So let's try to recap. This was the length of the string that I just made. And these are the two extremes that they could possibly take. And then I said, it can't be this perfect square or this one. It can't be either one of them. And it's in the middle between them. Is there any other perfect square in between? No, they're consecutive perfect squares. So since they're consecutive perfect squares and not equal to either of them and in between, there's no way it could be a perfect square. So I can conclude that P squared plus B is not a perfect square. Then what can I conclude? Is that string in the language? No, it can't be in the language because it's not a perfect square, like we just said. So it's not in L2. And so now I can say L2 is not regular. Cool. So this proof's in the book, so I would highly recommend looking at it. But the neat idea out of this was to look at the string that we get and say, could it possibly be a perfect square? And then we looked, what is the largest value you can take on? What is the smallest value? And then show that consecutive perfect squares just lie right outside of that range. And therefore, it can't be equal to either of them. Okay? Any questions about that? Because the next one's going to warp your mind. Not that much, but it's along those lines. Okay. Because I hope you're starting to see that these regular languages, these DFAs, aren't really that powerful. Like, I can't even check whether something's a perfect square or not. Something that, like, is very simple for a computer to do, which is quite amazing. All right, so let's look at 0 to the n, where n is a prime. Please, does anyone not know what a prime is? Okay. Someone at one of my recitations asked, what is a prime? At the very end, too, after I did this. So let's get it out of the way. Remember, prime are only divisible by 1 in itself. Right? That's what the definition of a prime is.
So by the definition, is 1 prime then? Because I know some systems don't consider 1 as a prime.
I'm not worried about that here.
Okay.
If you add finitely many strings to a non-regular language, it's still non-regular. I'll let you prove that, but I'm not worried about that here. But good point. Okay. So what's my first step? And I have to say it's not regular. what's my first step?
Assume it's regular.
Assume it's regular. Awesome. L3 were regular. And then obviously there exists a P for L3. All right. And so, what's my next step?
Choose a string.
Gotta pick string. So I'm gonna leave a space for a reason. So I'm gonna choose W equal to, and I swear, some students do this, 0 to the P. P stands for prime, like it stood for perfect square over there. So therefore, this is in the language and has length at least P. Can I do this? Please say I can. All right, well, what do I need to do? I need to find a prime at least P and make the exponent that. Can I guarantee that there's a prime at least P?
Oh,
Because if there aren't any, then I can't guarantee I find such a string. Yeah, there better be. How many of you know that the fact that there are infinitely many primes? Okay, so there are infinitely many primes. I'll just assume that offhand. Can they all live less than P then? Can they all be less than P? No, P is finite, and so therefore, since there are infinitely many of them, there have to be infinitely many more above P. Could I just pick one of those? Possibly. I need to find a prime, and it has to be of length at least P. So can I pick some prime at least P? Yeah, it seems like a worthwhile attempt. So I'm gonna let R, so R here is gonna be the prime that I want, or a prime that I want. So let R be any or a prime at least P. And I'm gonna let my string be 0 to the R. So let's make our check again. R is prime, so it's in the language, and it's at least P, so we're good. But I'm gonna make a very, very slight modification, very slight. And we'll see why I make this modification. It's absolutely necessary here. I'm gonna make it at least P plus 2. But we still gotta check. Is there a prime at least P plus 2? Yeah, just like there was one at least P, there definitely is one at least P plus 2 because there are infinitely many. Okay, well, it's still in the language, and it's still long enough, so we're fine here. Okay, well,